Thank you, Hussein, for very, very kind words, and thank you all for taking the time from your busy days in coming here. I have been doing networking, and I've been associated with the networking space for give or take almost 3 decades now. In fact, when I look back and think about what I've been doing in my professional life, I think networking is the only thing that I really know. So if I'm not doing networking, I'm probably not very useful. But also because I've spent quite a bit of time here, just like many of you. I'm sure you look back and you think about what you have done in all this time. I've been thinking quite hard about what networking has done for us. And I'm still amazed, even though we live in the middle of it, all of you do, I'm still amazed with how fundamental networking has been to how we live, how we connect, how we consume information, how our daily life is today, right? And when I think through it, what I found interesting is that, at least as far as I have been in this space, and maybe there were other inflections that happened before, I find that there are 3 distinct eras that networking has gone through. I call them, for the ease of it, 1.0, 2.0, and 3.0. We are just at the beginning of 3.0, and I'm actually going to walk you through that and explain what I mean by these eras. But what I find is that in each of the era of networking, there was always a killer app. And that killer application ultimately drove significant inflection into networking technologies, into network operations, into the use cases of network and how network gets consumed. And as a result, the technology itself evolved in step function ways. So let's start with networking 1.0. So this really started, back old days of telephony, and it has grown over many years. The real killer application of networking, when it really started, was really connectivity. It was all about connecting people to people or places to places. That was the killer application. And that killer application, sort of evolved over time. It took various forms, from circuit switch to cell switch to label switch to lambda switch to packet switched, and it's still happening, so on and so forth, right? But the common characteristics that you see with this phase of networking is that it's really about connectivity. It's about people on 2 ends of the connection or places on 2 ends of the connections. And in the early days, interestingly, there's one thing that we talk about a lot, things. Internet of Things was not a thing at the time. And we're talking about pre-internet, 80s, potentially 70s, right? Where it was really about connecting people and places because things were still not quite there. And it took various forms. Now, this network actually had some pretty clear characteristics. It is really best described by the OSI 7 layer, where there's clear layering as to how this connection happened. There was clear description of client-server relationship between these layers. And the 2 endpoints that you were connecting could really exist in one layer of the network. They couldn't actually go across the layers. And the layers to each other were more or less opaque. And there are a lot of good reasons why that happened. One of the biggest reasons that this clear layering was important was because in those days, CPUs were not very powerful. So it was not real easy for the control and the management plane to really reason through the layers because they did not have as many cycles. So it's very important that you treat the other layers as opaque and really deal with the layer that you're in, right? And that's how most of the network was built in those days. I'm sure many of you have lived through this for many, many, many years. There's another characteristic that was pretty distinct during that time. So if you think of what you were connecting, either people or places essentially lead to an n-squared relationship of how many connections you have. Now, neither people nor places actually grew very rapidly, on a relative scale. So our biggest friend was Moore's Law, because every 18 months or so, we actually got network technology that were about double as efficient, as capable, or as capacity that we were able to deploy, right? So the main approach that we took for networking was what I call scale up. We all built these very large chassis-based systems. They allowed various forms of connections in them, increasingly multiple forms of connections. We used to call them God boxes. It was IP over Ethernet, over ATM, over so on and so forth, various forms of those. Every 18 months or so, we actually got a capacity upgrade on these boxes, which actually allowed us to keep up with the new capacity demand that we had in our networks. And more or less, once they deployed this chassis, they remained there for quite some time. Their numbers did not increase very rapidly, but their capacity obviously grew, but the number did not increase very, very rapidly. These boxes were also built with very closely coupled systems that kept data control and management plane very close to each other. They're built more often than not with proprietary systems, started all the way from the ASIC that went into the box to the low-level software that controlled those ASIC to ultimately the control and the management plane software. And the very interesting part in that era was that standards, even though they existed, did not always guarantee interoperability. Data plane mostly interoperated, control plane depended. BGP of two suppliers did not always talk to each other or mean the same thing. Management plane was very far from actually interoperating. The CLIs are different, NMSs are different, there weren't clear APIs on the NMSs. Applications, those very few ones that actually use network, they viewed network as pure connectivity layer. It was dumb pipe. Like that's all that network did as far as applications are concerned, and networks themselves did not care too much about what the applications were doing on them. And the most interesting bit that those of you who are in the networking space for say less than 10 years, if you look back, you'll find surprising that in those days, if you were starting a tiny project in your garage to build a network system of any sort, it was immensely difficult because there was no thing called merchant silicon. You couldn't really go and get a little motherboard and start doing stuff. There wasn't that much of an open source networking stack either. Like there was FreeBSD, which had a decent networking stack, but remember, this was before Linux was a thing, right? So your only option of building network was either to work for a large company that was building networking systems or buy from them. Those are really your two options. And that's what most of the network operators did. They went to one of those companies and they mostly bought things from them. It was a fairly closed system at that time. The other thing that also signifies this time was how these networks were operated. Now, one of the good property of scale up was that the number of elements that you had in a network did not scale by order of magnitude over time, because those same systems allowed you to grow capacity without having to add more systems. So more or less, if you were an operator and if you're trying to figure out how much OpEx I need to spend in this infrastructure and how I want to run that, you essentially associated X number of operators with running this infrastructure. Those, by the way, were highly skilled operators because they were expert in this specific sets of networking technologies, often from specific vendors, and often with specific domain. And that model actually worked because, again, your number of elements in the network did not grow that much. So these experts were highly valued as they actually knew how the systems worked inside out. And they were at work every single day running this infrastructure. And that went on for many, many, many years. I would say, a good 20 to 30 years from 70s to early 90s. And that model reasonably worked. Many of us have actually built infrastructure or network that followed exactly that model, and we have been successful in building networks and businesses in many cases, right? Now came a very large inflection in really 1990s, early 1990s, mid 1990s. And that led to what I call networking 2.0, which has very distinct properties that are different from what happened in networking 1.0. That inflection is really called public internet. It's when internet became ubiquitous to how we live day in and day out. The need for network and what network did completely changed. It obviously started out with Netscape and other products like that, but the real inflection started happening when we got multimedia applications like YouTube, like Netflix, Facebook, Instagram, coming into picture, enterprises moving to video conferencing that were built on internet-based products. As that happened, what really drove the growth of network were not people or places anymore, because they don't grow that fast. It was data. Data has an uncontrolled growth. It really depends on what's producing it and how we're consuming it. It's not limited by how fast people are born or how fast civilization spreads. So it had much faster growth. In fact, many of us in this room have lived through these early days of many of these applications, and many of us have been have looked into dashboards where our traffic doubled or more than doubled every year. That, by the way, was the real inflection. Like if you look at it right now, 3.5 billion users, actually it's closer to 4 billion global internet users and growing. Still, billion or 2 billions left out who are not on the internet, so it's going to keep on growing. 1 billion hours of YouTube video watched every single day. 2 billion plus monthly active Facebook users, I believe it's growing. 2.5 billion smartphones out there. Average internet connection speed has gone up from 3 megabit per second in 2007 to 20 megabit per second in 2017. And if 5G actually happens and it delivers everything that we want, it's going to be a few hundred megabits per second for all users, right? So those of us who are looking at our dashboards, I remember very well the early days of YouTube, right? And we looked and got really scared with this hockey stick growth of demand. A light bulb went up. Like if your demand is doubling every year or is faster than doubling every year, well, Moore's law is just not going to keep up. Your whole idea of scale up doesn't really work because you really can't wait for 18 months or 2 years to get the next better capacity or better speed interfaces on your systems that you have, right? So we had to think different. We had to think different because we had no alternative. There was no other way of keeping up with the scale. And what has happened since then is that ultimately, where the data gets generated has significantly increased. These are just massive warehouse-scale data centers. And the way they get consumed has significantly scaled, which are increasingly with 4G and 5G handsets and smartphones, where people have ability to consume really high-capacity data or high-bandwidth data into their handsets everywhere in the world. So the need for this scaling keeps on growing. And the answer that many of us came to, and it happened almost simultaneously in multiple places, was that we went back to an old way of scaling network, which was called Fabric. It started out in data center, and then increasingly it moved into other spaces of the network. In the case of Google, there are many generations of this Fabric that we have gone through, called Firehose, Saturn, Jupiter. You must have heard of many of those in Amin's keynote yesterday. But increasingly, we took that same concept and we moved them to our WAN. B4, which is our SDN WAN, is built with the exact same concept. And increasingly to our Internet Edge. Espresso, which was the other SDN that we did, also uses the same concept of building Fabric for scaling the infrastructure. The property that this architecture really has, once you start thinking about it, is that it scales, the number of elements in this architecture scales with the demand growth. Very different from scale up, where it was more or less static over time, right? When that happens, you realize very quickly that I really cannot operate this infrastructure the same way because I don't have enough skilled network operators out there in the world to scale with the demand that I'm dealing with. So I can't really treat my network as pets. I need to start treating this as cattle. I have to manage the fabric and not the elements themselves. The other thing that happens, which is a property of scaling of any systems, is that the number of failure events that you're going to see in your infrastructure is almost linear scale of the number of elements that you have. So while you solve the problem of scaling with demand growth, you inherited this new problem that now stuff breaks more often. So let's go through a very simple example of this, right? And it's sort of interesting to put this in perspective as to how often these failures can happen. So take a very reliable switch that you can buy from the market, say MTBF of 30 years. If you had one of that in your wiring closet, this thing is basically not going to fail. You can have your whole network on that for a good lifetime, right? Try building a fabric with 1,000 of those. And if you do the math, you'll find that one of your switches are going to fail every week, statistically. It's not true every week, but statistically, you're going to see one failure every week with the most reliable switches that you can buy in the market. Now think of one of the switches which has maybe 24 ports of 10 gig or 100 gig or 400 gig, right? And you buy the absolute most reliable optics that you can find in the marketplace. Let's say it has an MTBF of 50 years. Like, one of those is never going to fail. Do the math, and you're going to find that every day you're going to see one failure in your fabric. This is sort of what Hossein was talking about, that statistically insignificant becomes a real thing when you're dealing with large number. And scale-out has this exact property, because in scale-out, because you're throwing number at the problem of scaling, you inherit all these challenges with reliability that comes with that. And you start realizing very quickly that there is no way that I can operate this network in the classic way of dealing with unreliability of system. I have to think my whole architecture that essentially assumes that my parts are unreliable, but I'm going to build a reliable system with unreliable parts. And the only way to do that is really software. So this is really the genesis of SDN, right? The reason that SDN happened was not because some of us were sitting in a room and said, wouldn't it be really cool to run software outside of the boxes? That was not the genesis at all. The reason that it happened was because we had no other way of managing the system at scale. That was the only option that we found, at least at the time, right? So that was the genesis of how SDN happened, at least in Google, but I've had the same conversation with many of you, and I always hear very similar stories as to how we ended up there. Now, if you followed that train of thought, and if you came to the same conclusion that we did at the time, that, look, if we're really going to run the system, it has to be run by software, then few of the other design principles just follow through. And there's sort of the logical follow-through of that conclusion that you came to, right? The first one is, if I'm going to build a common software to run the system, the underlying elements must look the same from software perspective. They can look totally different from hardware perspective. But from software perspective, they must look the same. So they must be built with around the same software system that you run on them. They must have well-defined APIs and well-defined data models so you can change the elements underneath without having to change the whole software system that manage them. It becomes critically important that you actually have well-defined APIs and data model that are not vendor-specific or that are not implementation-specific, that actually can span vendor or implementation. It must be programmable at every layer. Why is that important? That is important because this is the first time in how we have been thinking about networking at that point in time, where we realized that you cannot really have reliability by essentially planning for a certain failure. Your system has to react to failure modes that you may or may not have seen in the infrastructure. And your response to one of those failures has to be your ability to program at the right layer of the system. So if you are trying to recover from something where a couple of milliseconds of packet black holing is a problem, then you can't address that by just programming the management plane, because management plane is not fast enough. You need the ability to program the data plane. But if you're responding to something where it is a security breach that has happened because of a failure or because of a wrong ACL push, you don't need to touch the data plane. You can do that just by programming the management plane. But it is important that you have the abilities to program all of them, and the underlying system must offer that, right? That is what I ultimately view as the definition of SDN. That systems that allow programmability at every layer, that has clearly defined APIs and data model, and there are clear separations of control data and management plane. So we actually can reason about what we program and when we program it, right? So that's sort of my definition of SDN. The other thing that comes into play in this world is that there's this big change that happened from scale up to scale out, where we all of a sudden are dealing with this explosion of new elements that are coming into the infrastructure with capacity. Any one of you who run a large infrastructure, I'm sure you have come to the same conclusion that I have, which is operation is really an optimization on three axes. It's a trade-off. It's scale, reliability, and efficiency. And it's reasonably easy to hit two of three. And you can go through examples, right? You can buy two of them by just spending more money, but you won't get efficiency as an example. It is very, very hard to get all three of them. And as operator, we strive to get all three of them. So what we realize in this scale up to scale out is that what really happened is that we traded off CapEx with OpEx. Because in the olden world, we had this large chassis, and we could add more capacity, but we're really throwing CapEx at the problem. In this new world, nothing is free. There is no free lunch, right? So we actually can keep on using these fabrics for a longer period of time because we can scale them out. We can add more elements in there. But the price that we pay is that all of a sudden our operation cost has gone up in the form of more failure, more things that we have to manage, more repairs, more people that we need to operate it. So again, the answer that we found is that in this world, the only way to hit nonlinear scaling of OpEx is by automating everything. It was not automating pieces of it. It was not automating, the config update or so on. It was the whole life cycle. It's the whole life cycle of the system. Starts from planning, goes all the way to repair, and finally, removing the things from the network. Automate the whole ecosystem. What is also important, just like SDN, automation to us was not really a choice. It was a matter of survival because we just couldn't keep up with this infrastructure if we did not go on with this approach. So just like SDN, automation was sort of a necessity of the day. It was not because we're very smart and we're thinking of very smart architecture. I mean, there are a lot of smart people that ultimately came up with the answer, but the answers were driven by this problem that we were trying to address. So that brings me to, and that scale out world has delivered lots of benefits to us over a long period of time. And we really have evolved that architecture over many years. It doesn't quite look the same way as it looked before. But as we're doing this, and as we're enjoying scaling this infrastructure, and actually innovating quite a bit around software-defined network and at every layer of networking, a third inflection happened. And it is probably the largest inflection since internet that has happened to network or any compute infrastructure in our career, and that is called cloud. Ultimately, public cloud and increasingly hybrid cloud change expectations on how applications are built and how applications are delivered. Increasingly, we use mission-critical consumer applications as well as mission-critical enterprise applications that are delivered from cloud. Like, I'm sure many of you came here driving using Google Map or something similar, Apple Map. We do our bank transactions and our payment on our phone. Increasingly, our enterprise applications run everywhere and uniformly. At Google, we have this enterprise architecture that we call Beyond Corp. And the whole premise of Beyond Corp is that a Google employee can be on a laptop, Google laptop, and be anywhere in the world, in a cafeteria, in a hotel, a conference like this, or on an enterprise network, and they'll have the exact same enterprise experience without having to do anything else. They don't dial into a VPN, they don't do anything. They just open up the laptop and they get the same experience everywhere else, including security. Now, if that's the expectation that all of us have with our infrastructure, then we also have an expectation that our applications work as reliably, meeting SLA, with the same security everywhere, right? So if you think through ultimately what are the fundamental things that cloud of any form, public or hybrid cloud, really offer to us, and how they change how we write applications, you'll find that there are 4 characteristics that we follow. And interestingly, those 4 characteristics are the same that you have in any infrastructure that you rely on day in and day out. They are fungibility, reliability, security, and ubiquity. And you'll find that you can apply those same characteristics to running water or electricity. Because any infrastructure that you rely on for your mission-critical applications must have this behavior. What does that really mean? Fungibility. Like if I have an application and whether the application is running on my on-premise data center or in one of the public clouds, as a user of that application, I actually don't care. I want the exact same behavior from the application. So compute and storage is really a fungible resource. Reliability, it must be there. We have grown to expect when I'm driving, whether here in US or Mumbai in India or Rio de Janeiro, Google Map just works. We expect them to be reliable wherever we're going. It must be secure. I mean, we expect that when we're using these applications, no matter where we are, they're secure. And ubiquitous, because that's really what cloud does, right? We actually expect ubiquity wherever we go. Now, if you walk through this architecture, and if you think of How do you deliver these characteristics? Of course, compute and storage architecture has a lot to do with it. But what you'll find is that networking has an absolutely critical role to play in this happening. Fungibility. When you are really using compute and storage infrastructure on-prem or off-prem or between multiple clouds, what makes that possible is high bandwidth and predictable latency on your network. It could be inside your fabric, or it could be spanning on a hybrid cloud infrastructure. That's what ultimately makes it possible. That's why you can pool a set of storage SSDs or a set of CPUs or a set of GPUs and use them as pool instead of allocating them for specific tasks. Network makes that happen. Reliability. The best way that we found to make things reliable is by breaking things into self-contained availability zone. I know Amin talked about that quite a bit yesterday. What really allows an application to take advantage of this different availability zone is network. Whether it is at the load balancing layer or whether it is at the L3 connectivity layer or even L1 connectivity layer, ultimately network allows your application to take advantage of this increased availability by breaking them into availability zone. Security, it comes all the way from visibility to containment to threat mitigation. If all your applications are using your WAR, that's the best place to find really anomalous behavior that you can detect by using smart techniques like machine learning. Network allows you to do that. And once you have it, you also have the abilities to go and enforce rules on your infrastructure, whether it's L3 or L7, it doesn't matter. And of course, ubiquity, that's the definition of network, right? So it is clear that to get to this new world of applications where applications are cloud native, network has a very critical role to play. I often hear from people that, oh, when we do cloud native applications, we just don't need network. Well, it's the exact opposite. You need a network that allows you to be cloud native. You just may not see it. That's what I call invisible infrastructure, because it has all these characteristics of offering you what you need without you having to really design it that way, because somebody else has done it for you, right? Interestingly, in this world, we inherit all the good things that we developed in Networking 2.0. They're all applicable, but there are few other things that are very distinct that happens in this era that was not the case in Networking 2.0. The first one being, if you're really going to hit all these four characteristics, you really cannot differentiate between physical and virtual networking. Let me give you a concrete example. So you have a Kubernetes cluster. It could be Anthos, it could be your own Kubernetes cluster that you run in your private data center. You also want the ability to run some of your workload in public cloud, and you want them to move fungibly between this on-prem and the off-prem. So if you start thinking about networking, on your on-prem cluster, you more than likely are running a physical data center network. It's probably consists of switches and so on, and you have potentially SDN that allows policies and routing for the traffic that is coming in and out of this Kubernetes cluster. When you're running the same thing on public cloud, you're most likely interacting with the VPC. You have equivalent characteristics in what things are doing, but it's virtual network. It's not really physical network. Or at least you are not managing physical network, right? If you want true fungibility, this network must look the same as far as your applications are concerned. They must look about the same, right? They cannot look very different. When it comes to load balancing or firewall or packet processing, they must look the same. This was not a requirement in the previous generation of networking. This is a very new requirement, right? With that, few other things happen. So not only is the line between physical and virtual network blurring, the line between on-prem and off-prem network has blurred. Again, if you can use the same example, you'll notice that on-prem and off-prem networks are the same thing, mostly. Happening across the board with things like SD-WAN connecting to cloud and really extending your on-prem network to off-prem, right? So they're increasingly becoming the same thing. And the difference between public and private network has pretty much disappeared, because you tend to use both depending on where your applications are and how you use it. If you trace any application that you ultimately rely on, I can guarantee you that it traverses some bit of public network and some bit of private network. And for those applications to work with SLA, the whole thing must work, right? Pretty unique requirements on the network that we're trying to build. So how do we address this? There are a few, again, best practices that starts coming out once you start reasoning about network that way, that really physical and virtual are not two different things. Like when you talk about SDN, we're not really talking about a virtual infrastructure, we might be talking about physical infrastructure and vice versa, right? So the first thing that you realize very quickly is that my network infrastructure must be really disaggregated. When I'm talking about packet processing or flow processing, whether it's in L3 or L7, that packet or flow processing might be happening in a network ASIC, either in a switch or router or in a network interface card, somewhere in a server. Could be happening in a CPU, could be happening in a hypervisor that's running in cloud. They all offer, give or take, the same function. The performance might be different. So when I write a network application, the network application should be reasoning about performance, but not about how they're processed underneath. That's the only thing that I should be reasoning about, right? And the only way that you really can do that is by building a very clear abstraction layer above this forwarding plane. This abstraction layer must hide the implementation details, whether it's physical or virtual, from the network applications that we run. The second thing that happens is that your network applications must be very modular, and it actually use all the best practices of cloud-native software development, where ideally they're microservices. And the reason being, those applications may run on a network device, a switch or a router or so on, or they could very well run on a public cloud instance somewhere, doing the same thing. Like you could have a firewall that is a physical firewall function, or it's a virtual firewall function someplace else, right? So unless you have written the application with this assumption that it is not going to run in this specific environment, but it can run in multiple environments, you'll not get there, right? So it must be modular and microservice-based. And a third is really an extension of the principle that we derived in Networking 2.0, the clear definitions of APIs and data model that gets carried through. And increasingly, those APIs are applicable to both physical devices, but also virtual instances of networking. Examples like forwarding plane APIs such as P4 or SI, control APIs such as GDB or Sonic, and management API, GNMI, GNOI, parts of Sonic, right? As an example, right? Must have clear API definitions and clear data model at every layer of the network if you're really going to build these applications that way, right? But then another thing that starts happening in this world, which is, network, one would argue that network has always been open because things have to connect, right? It depends on your definition of open. Yes, open standard, network has followed open standard for actually a long period of time. But increasingly, you see use of open source software, open APIs, open data models at every layer of network. And the reason being that as we start reasoning about disaggregating our network implementations, the places where you need open definitions of things, APIs and data models, are not just limited to the boundaries of a system at which we drove standardization before. It is within the layers. It is within the layers of how I define a data plane. P4 and P4 runtime is a great example of that. Like I actually have a common way of describing what a data plane does, irrespective of whether it runs in a switch, in a network interface card, or in software. I have a common definition. How I configured these things, a good example is OpenConfig, very close to me. Some of us started building this concept many years back. And it's an example of where ultimately it's describing the behavior of a network function. It doesn't matter whether it's physical or virtual, it's equally applicable. And then more interestingly, increasingly orchestration of these network functions. As I described, as you start writing these network functions as containerized microservices, whether they're getting orchestrated inside an appliance or whether they're getting orchestrated in a cloud, increasingly, we're using common open source orchestrator like Kubernetes, like Istio, like Service Mesh for describing the network behavior. So I believe very strongly that standardization is now happening in open and it's happening in code. Open source is the place where standardization now happens. And this is a journey that we're just starting, and I believe that this would be the norm as we go into building network. This actually increases innovation velocity for all of us, but it also allows us to start building from what are de facto standards. So we don't have to start figuring out what specification that we start with for an API or a data model or an orchestration and so on, right? So I believe that's going to happen. Now, the third bit that is becoming very interesting with networking 3.0. So I talked about how automation was quite important for networking 2.0. Now, if you walk through the automation journey, I break it down into sort of 5 distinct eras of automation, of which we started with human-driven. Most of the network was human-driven. Workflow-driven was when we took our mops from Word docs or text files and we turned them into Python codes. Many of us have done it in the past. That was the first step towards automation. We automated pieces of workflows, not really lifecycle, right? That really started happening in 1.0, became gathered pace in 2.0. Event-driven is where we actually look for high-quality signal from the infrastructure itself, mainly events, and start workflows based on what those events are. This became a norm, again, with the scale-out network 2.0 architecture. Many of us have deployed automation system that does exactly that, right? But one of the interesting things that happens when your network is application-led, a lot of the intelligence that you gather as to how your infrastructure is behaving is not in the network layer, but in the application layer. Simple example, you might have packet drop on your network layer, some level of packet drop. You might have an application at a higher layer that is very tolerant to packet drop. And having that low level of packet drop might be completely fine for this infrastructure to work because it does nothing to hurt the SLA of the application that you're running, right? So if you try to build intelligence just looking at the network layer behavior, you might be under-optimizing or over-optimizing your network depending on which axis you're optimizing it in, right? So we have no option but to look into this additional layer of intelligence that comes from the application layer. Now, if you think hard, this is really a violation of OSI 7-layer principle, right? But we now have compute that actually can do that. It has abilities to consume this massive data, make sense of them, and provide signals that are very actionable, right? And we see that happening or starting to happen in network infrastructure. I call that machine-driven. So in machine-driven, you really gather as much of information about how your network is doing from network and applications, everywhere where you get interesting network-related information. You make sense of them by using smart algorithms, oftentimes machine learning, and you create high-quality signals that are immediately actionable by software. We built this SDN called Espresso, where a lot of the intelligence that comes in Espresso actually comes from the application layer behavior of how Google services behave. And we take this behavior to create signals to ultimately guide the network as to where this traffic should egress, or how a tunnel should be formed, or how a repair should be done. Because we not only gather signal from the network layer, we gather signal from all the layer, right? That's machine-driven. I believe that machine-driven is a feature for networking 3.0 that we all must think about developing and building if you're not already thinking about. But once you go there, then you start thinking, there are a lot more complex systems than network in many cases that actually have gone through this exact same evolution. If you use the car analogy, right, machine-driven is cruise control approximately, right? That the cars are at that point self-driving within a certain boundary, right? If cars can go to fully autonomous, or if planes can be fully autonomous, why wouldn't the network be fully autonomous? Isn't it the standard progression of how the networks work? And I very strongly believe that is possible. There is nothing with network as a system that stops us from making it fully autonomous. Now, it doesn't mean that every network will become fully autonomous, because if you are going in the direction, you have to start building the network from the scratch with that idea. Like many of us, we have inherited legacy network where they were not built with automation in mind. And you can't get there. You can't get there because it doesn't have the right characteristics to automate them. But if you start with the idea that my network is going to be autonomous at someday, where there'll be no human that touches the network, you would apply the design principles that I have been describing here, right? So one very important design principle that actually falls out, if your goal is to build self-driving network, and I believe very strongly that if you're trying to make our whole network self-driving will fail, we have to really pick a domain, ideally a greenfield domain that you're newly building, And we go after that in turning that self-driving, because you actually can't start with all these good principles. You don't try and force fit them after the fact, right? So one principle that comes out, at least jumps out to me in doing self-driving network, is intent-driven networking. So what does that really mean? So what really means is that I have the ability to completely describe the intended state of the network in an object model, and that object model is persistent. That's the desired state of the network. That's where the state of that's where the truth about the network actually exists. An example of that, we have built this model at Google. We call it Unified Network Model, or UNM. UNM is how we describe intent of our network. What we expect the network to do, not how it is ultimately implemented at the lower layer, right? If you are able to describe your network intent with an intent model, then you can build a system that actually takes that intent, compiles it, parses that into states that the network must inherit, and actually has abilities to keep the network in that state, or always tries to take the network very close to that intended state. In order to have this closed loop system, you also need really high-grain, real-time, high-resolution telemetry from your network system. And it really is possible. The only way that you can do that is by having very high-resolution streaming telemetry that always streams the state out from the network. So you actually can reason about whether my network is in the intended state or it is deviating from the intended state, and therefore I have to take actions. So it has to be a closed loop system. And once you build a closed loop system, you actually can start making the reasoning about the system smarter and smarter. Now, we have been able to build this closed loop system, but I would fully admit that we're nowhere close to really getting to a self-driving network. It's absolutely our goal, but we're nowhere close to getting a self-driving network. But we actually have this closed loop system where we can describe the network with our intent. We can compile the intent to turn them into states that we actually push to the devices or the elements or the software. We stream all of the state from that, and then we can compare how the systems are and close the loop where it's necessary, but it's not yet super smart. With that system, you can then start thinking about, okay, if I have that and I have all this data that is coming in, including data from application layers, I can easily start throwing from rule-based reasoning of the data to machine learning-based reasoning of the data. In some cases, it will be neural network. In some cases, it could be reinforced learning. And most interesting is that no outage in your infrastructure should ever go to waste. Every outage is an opportunity to train the system to detect that next time around before it happens. The holy grail of any infrastructure is ultimately getting MTTR to 0. And the only way that you can get MTTR to 0 is by doing predictive maintenance. You have to predict that something is going to happen, and you have to remediate before that outage has happened. That's the only way that you can ever get to an infrastructure where very few failures happen. And the reality is that it is not possible to do by humans, because it takes us some amount of time to reason about that, and by that time the outage has grown, right? So it must be a fully automated system that actually goes with this approach of really maintaining the network state with the intent. There is one other beautiful thing that falls out in this architecture. So if you are able to describe your intended state in an object, then you have abilities to validate that object before you compile, and you have abilities to roll back that object when things go wrong. That also means that you really reduce the probability of failure in this infrastructure. It is never going to be 0. We're always going to have bugs, because every system has bugs. But as a system design principle, you're actually reducing the probability that your system is going to fail, right? So I believe very strongly that as we're going into this world of application-led networking, we have to walk from the SDN-based approach to increasingly intent-driven network and apply this very powerful techniques that we have developed in machine learning and automation in there. So in summary, in networking 3.0, increasingly, the OSI 7 layer of client-server model of strict separation between layers, they start to fall apart. In fact, you now have abilities to consume information from all the layers to make smart decisions, whether those information are coming from your optical system that is showing large errors, or it's coming from application layers where you're seeing RPCs not completing. They're all useful information for you to reason about how the network is doing and make decisions based on that reasoning. Application hour optimization of every layer is a norm, and it doesn't matter which layer you're optimizing. You might actually be co-optimizing multiple layers at the same time. You might decide that this is best done at layer 7, but that has a large enough aggregate that I should be doing at layer 1 and not layer 7. So increasingly, we can't think of them as fully decoupled system. Supervised and reinforced machine learning is going to be a norm. I believe that if you look at other systems that has gone through the same steps of automation, car is a great example. Supervised and reinforced machine learning is going to be a norm in the way that we do control and management and design and automation. And last but not the least, I've had a lot of conversation with many of you, through my career on how do we ensure that we are not only introducing all these technologies, but we are able to operate them the right way. And the approach that you take is that you absolutely need the knowledge of networking. It's akin to saying that if you are flying a plane, you must know how the plane works. Every pilot knows that. But increasingly, a large component of that work is actually running software. So we need folks who actually know how to operate software systems, but have the knowledge of networking so they can apply that as they run software system. And this is the world that we are already living in, and I believe that this is the world that many of you would live in for quite some time to come before the next inflection hits us. And I have no idea what that next inflection is, so I'm very excited. I'm waiting for it. And with that, I'm going to open it up for questions. Thank you very much. Questions?
Hi, thank you. Interesting talk. Louis Lee, Google Fiber. It might be obvious to you why we need a high resolution telemetry, but can we discuss that briefly?
Sure.
What scenarios would require that? What would you miss if you don't have that?
Yep.
And you said something about a stream of state. Are you streaming just event alerts, or is it just a constant state kind of thing? And what about the threshold monitoring? How would that play into this?
Okay, great question. So the question is, when we're streaming telemetry, what do I actually mean what we're streaming? In ideal world, you want to stream everything that happens to a network system in data plane and control plane and management plane. Impractical, because you may not have abilities to stream all of that out, but you want to get as close to that as possible, which also means certain things with how we design networking systems, right? So if your goal is to stream as much of information as you can from data plane, then you have to design data plane differently, where you are not necessarily relying on pushing the packet up to the management layer to get it out, right? You need the ability to stream it out. Why do I need that? You need that because when you start reasoning about the root cause of a failure, and you want to react to the root cause of a failure, you want very high resolution events. I'll give you an example, right? We often grapple with this, what we quote unquote call flapping that you see in our optical fiber. And when you start looking into the details of what that flapping is, you realize that they're not all the same things. And the reactions to them are not the same. And you really find that out by really looking at the time resolution of the event, how often they happen, what is the frequency, and so on and so forth. If you don't have high resolution data, you may already have masked the actual root cause before you have the abilities to go get there. So if you're really going to do that, there are a couple of things that you need. You need a common way of streaming the data out. In our case, we use open config streaming to actually do that because it allows us to take data plane as well as control plane state as you go out. You need a collector that is able to take all this data and actually keep the data, the historical data that you can then go back and process as it later happens. And finally, you need a control plane system that actually can do real-time processing of the data, so it can react to it, right? So you need this whole ecosystem in there, which we actually have built in the Google Production Network. Your second question was, I talked about how the intent system takes an intent and compiles network state and pushes that into the network. I intentionally use the term state because that state can be a piece of config. You might decide to compile that into a piece of config that you push into a network device, or that state could actually be a forwarding state that you push into a switch or a silicon. Or it can be actually a sub-intent that you push into a part of the infrastructure, right? So it could be many things, and that's why I use the term state. How durable that state is, it actually depends on which layer you're pushing it to. Great question. Thank you.
I've got a question over here. I'm going to try and ask a question I asked yesterday and didn't quite, is what happens about Google's network itself becoming a single point of failure? So the guy yesterday talked about B4 failing over to B2. B2 is internet-based, couldn't handle the traffic, and we had chaos for several hours. Do you end up having to run a red team, blue team? Because even as Google's going to get bigger, the public internet resources available to handle that failover are not getting bigger at that same size.
Yep.
And if I look at now abstracting out from you, Facebook, AWS, Azure, and a couple other big players, if I look at each of those as a single monolith with a single point of failure, if one of you goes down, there's no place for it to fail over to.
Yeah.
This concerns me. I'm sure it concerns you. But how do you engineer for that problem? Yeah. You have a sorcerer's apprentice problem inside your network. Does just simply a quarter of the internet disappear until we can fix it, or right. Is there a
right? We have learned through our mistakes of our designs, as Amin shared yesterday, right? And the best principle that we're applying in our designs is that we are trying to rely on global system as little as possible, and increasingly in the systems that we design. And this is actually a change in approach over the years because we've learned from lessons, right? That we increasingly design non-global systems. And where we have global system, we design it in a way that when the global system fails, the underlying non-global systems can still operate. They may not be as reliable, they may not be as optimal, but they're very reliable, right? So I'll give you an actual example of this as we have done. I don't know in what details went through the Espresso architecture, but that's a good example, right? In Espresso architecture, we have this global optimization that allows you to optimize how traffic flows across the internet from Google out. But we always build this assuming that centralized brain can fail at some point in time, right? So when it does fail, it falls back into the regional brains that are not globally optimal, but they're regionally optimal, give or take, right? And those regional brains can keep on operating independently of each other without relying on the global failure. Then you have a third fallback. And the third fallback is when even the regional brain fails, we still have abilities to forward packet relying on baseline infrastructure like BGP and IGP, right? To be very honest, we're not fully done with really reasoning through all of our infrastructure where we know that there is nothing global left in the infrastructure. But that's the design approach that we're increasingly taking. Because yes, if there is one thing that me or Amin will lose our sleep over, it's exactly what you described. So, yeah.
Tony Tauber, Comcast. So your earlier remarks about the scale of the network, things fail. And so even if you have a low MBTF, you multiply it, it still means regular spate of failures. And what I think generally it breaks down to is, faulty equipment, hardware, switchboards, optics, boards, or fiber cuts. So where you can automate the workaround, the mitigation quickly, and write your applications to adapt and all that stuff, it still takes a human being to fix every single one of those. So how does that scale?
Yep.
Every single one, you have to get a new device out there. You have to go patch the fiber.
Yep.
And,
great question. So historically, what we have done is that we have had a single MTTR budget. The MTTR budget was for, if you have a faulty port, go replace the faulty port. That was the MTTR budget, right? The approach that we're taking is that there are different MTTRs that you reason about, right? That if your software, it's not always possible. Like you can have a massive fiber cut where you don't have capacity, right? But in cases where software can move your traffic away from the failure, then your MTTR for actually doing the physical replacement can be very long. It's not infinite, but it can be very long, right? It's not days, it can be weeks now, right? So you don't necessarily need to schedule work the next day because it has failed, because you know that your software has reasoned about it and moved it out. We actually do that quite a bit. Like we have done that with how we do RMA, right? We actually don't necessarily respond to a down port immediately because with physical replacement, because we don't need to, right? We have, but the only way that you can do that is when you can very clearly have budgets that are allocated to what is my repair time and what that does to availability, right? So I would walk back from what is my outage budget, and then start allocating those budgets to these various things that I have to do. And what we always try to do is we try to give as much budget back to everything else with software. And that's the design approach. Okay.
Hey, thank you. Great talk. And the question is, you've talked about intent-driven networking, and I think we all agree we need to move to this direction. However, with regards to telemetry, the statement was you need to get as much telemetry as you could. Looking at modern systems, it generates terabytes of data a day with telemetry. Where are we with regards to intent-driven telemetry? If your intent object knows what your service should be, it also inherently knows what telemetry you need in order to validate that your operational state is in sync with your intended state.
Yep. Great question. So at Google, our configuration data model and our telemetry data model is exactly the same. It's open config because of exactly the reason that you described, right? We reasoned about it very early on. I think Anis is somewhere on the audience, and you can grab him for more of the reasoning.
I did many times.
Yes, exactly, right? So it became pretty clear that your intent that you're pushing into an element is how you want to get your telemetry back. So it's the same data model. We have abilities to consume telemetry at very high resolution. Now, I fully appreciate that. That hasn't been the case with everybody, because not everybody has a cloud infrastructure that you can throw at the problem. But what I would say is that increasingly public cloud is making it possible, right? And you see that with products that many of the vendors are building, where the telemetry system leverages public cloud to actually consume data at pretty high resolution. So it has become more viable now than it was for companies like Google and our peers. We had the advantage of having a compute infrastructure, right? So we have been able to do it for a while.
Thank you.
Thank you. Go over there, and then I'll come back to Arti.
Anthony Gervasi, Goldman West Telecommunications. You talked about building an intent-driven network, right? Have you published any case studies? Is there, for those of us who think that that's the dream and want to get there, where do we start?
Yeah. So yes, we actually have a couple of papers that describes this. I would say the one where we have the closest to description of an architecture that is fully intent-driven would be the Espresso paper. So I would recommend you read it. But even before you go there, what I found, so it's like SDN. Many of us landed into SDN without really designing it with that much clarity from the beginning. There was enough clarity in the best architecture, but not like we knew exactly how the best design of SDN is, right? For many of us, kind of the same thing happened with intent-driven network. We reasoned about it, and it made sense that that's how the architecture should be, and it sort of landed in there by building it, right? But looking back, there is a great intent-driven system that people use a lot right now that actually has a very crisp description of how it does it. It's called Kubernetes. So you should really read, what Kubernetes manifest does and how that really Kubernetes manifest is the intent, right? And it's a closed-loop intent-driven system. All the design principles that are used in Kubernetes are the same design principle that we used in building network, and it's not by accident, because we really inherited a lot of the best practices that Borg, which was the father of Kubernetes, actually implemented in our infrastructure. So there are a lot of similarities, but actually, I find that if you just read the Kubernetes architecture, you're going to find all these best practices there because they're implemented.
Thank you.
Sure. Arti.
Arti Iyengar, Arcus. question is on the 4 attributes that you laid out for networking 3.0. I'm calling it SURF, just so I could remember. The security, ubiquity. Where do you think we are as a community? Because if I look at 3.0, the bigger aspects of it seem to be operations. If you look at killer op, the killer app that you talked about in 1.0, 2.0, there were elements in the solutions that people provided that could be improved. You went from what vendors did or what software could do. In this case, it's very operational. So there are aspects of this which people who build networks like yourself need to incorporate for networking 3.0 to happen. And then there are aspects which obviously then you rely on the solution providers.
Yep.
And where are we with that? From a journey point of view?
Yep, great question, Aarti. I would say if we look across the industry, I would say we're in the early days. And let me walk you through a couple of examples of why I say we're in the early days, right? In most cases, when we write networking software, we still have assumptions as to where the software runs. Many of you are actually trying to change that model, but it mostly still exists, right? So it is not yet quite ubiquitous where you can say that, I had this OS that ran on my switch and or router or firewall, and I can reliably take that and put this on this edge cloud that I have that is a Kubernetes cluster. In most cases, it doesn't work, right? And in most cases, it doesn't work because we haven't built enough actual hermetic APIs around how these applications are. Like, what does it take for an application to run? What are its capabilities? How does other things interact with those applications? There isn't enough standardization on those for us. Most of our standardizations are still at the protocol interaction layer and not in the application interaction layer, right? So there is absolutely gap. Security is still thought of as a separate thing in many cases, right? Which I think is a mistake because in the olden days, we looked at ACLs and firewalls rule and so on, right? But the real thing with security ultimately is zero trust and actually knowing what's happening in your infrastructure and then reacting on it, right? Network allows you to do both. And so are we thinking from ground up to building security in our infrastructure where it's not an afterthought or it's not a separate product per se. This is not to say that you don't have products that are specific for security, you would, but every piece of networking product must think of security, which it doesn't necessarily do today. Like that's another good example. And then the last bit that I would say doesn't always get as much attention is automation. We have come a long way, to be very clear. I think in networking 2.0, in the last 10 years, we have made a lot of progress in building things for automation, right? But we still don't build things for automations where the assumption is that not only are we going to run this network, but there is lifecycle management. I'm going to do upgrades. I'm going to do repairs. I'm going to do refresh of things. Are those built into the way that we are building the automation APIs on the elements, right? That ultimately an operator starts building with, right? So I would say, we're making progress. We're going in the right direction. I absolutely see technologies that are starting to address some of those gaps, but we're still in pretty early days in going there. Thank you. I think I'm out of time. Maybe the last one.
Hi there, Tom Daly of Fastly. So I think everyone in the room should recognize the privileged place that folks who hold content have, because we terminate a portion of the connection, right, that faces towards the client, generally speaking. And that gives us a lot of access to very rich telemetry, a lot of the basis of which your networking 3.0 thesis hinges on. What advice would you give to network operators or best practices or concepts for engaging in the problem of information asymmetry, right, in this situation? Because a carrier does not have that rich telemetry data to consume to optimize their networks and ultimately help their users. So what opportunities in the networking 3.0 framework exist for that kind of maybe rich information sharing or some other means that hasn't been thought of to carry that engagement beyond the autonomous system boundary and through the entire end-to-end network?
Yep. Actually, it's a great question. It's very, very close to my heart. There are actually two aspects of this question, and both are important. One is content providers have a vantage point that necessarily the service providers or the edge providers have, edge connectivity providers. Flip side is also true, right? Edge providers have a vantage point, how well a radio network is working and how often somebody's cell switching that content providers don't have. And we have asymmetric information on both sides, and we don't have great abilities to actually share information. Google took a step sometimes back in trying to address a thin sliver of that. I actually would not claim it was as rich as what you're describing, but we have this product, this application called Peering Portal, where when we peer with someone, those peer gets very rich information on how their network is behaving against the Google content. They're private information for those peers, but these would be telemetry that they would not otherwise have because they don't have access to the application layer. Now, the problem with that approach, whether that approach is actually really liked by our partners because they use it quite a bit in making decisions. The problem with that approach is that it still doesn't define a common way of exchanging this information, right? And one of the things that I often talk to my team and think about, still the best between network infrastructure API that we have is BGP. And we have pushed BGP as far as we can, but it's still not as rich as we want it to be, right? And one of the reasons that we probably should rethink that is because when that was the richest API that we had, the endpoints of those APIs used to be routers. Increasingly, that's not the case. The endpoint of those APIs are software, even though they're speaking BGP. So clearly, they can have much better API than that, but we're still limiting ourselves into what we are. So I think this is actually a rich area of work that we need to collectively think about, because I don't believe we have the right API for the networks to talk to each other for networking 3.0, in fact, nowhere close, right? Because we are still blind to how each other's infrastructure is working, which is not optimal for any one of us. So great question. Thank you. Thank you very much for your time, and have a great conference.